So welcome to section 2.3. In section 2.3, we're going to take a look at evaluating limits again. Now, up to this point, we've evaluated limits in two ways. We did them numerically and graphically. So we made a table of values, found a pattern, saw what was going on. We made a graph, looked at the graph, tried to use it to evaluate the limit. We took a look at asymptotes and how that happens. We're also now going to take a look at solving limits, or evaluating limits, maybe that'd be a better word to use, analytically. And so basically what that means is we're going to perform algebraic techniques to find the value of the limit, and then evaluate those limits without having to use that table of values or without having to use a graph. Graphs and tables of values are awesome. They're really productive for finding them, but as we discussed earlier, they have a limitation, and the limitation is they really only work well if you can see a pattern in the numbers or see something on the graph. For example, just something really, really simple. If we took the limit of 1 over x plus 2 as x approaches 5, well, the limit of that is 1/7. Right? Now, don't worry about how I got that. We'll worry about that later. Let's just look at what that limit is, 1/7. Do you think that we could have a graph where seeing that the limit was 1/7 would be good or easy to see? Or do you think that we could have a table of values where we could see 1/7 in those tables of values? Like, I'm not even sure what is 1/7, like as a decimal, because that's what my table of values would give me. Well, 1/7 as a decimal is 0.14285714 blah 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 blah. It repeats. It's 14285714285714287, and so on and so forth. But I don't know that. And I can't just look at a table of values and see that. So what I need to do is I need to come up with some way that I can evaluate limits like this, some way other than having to rely upon always having a graph or a table of values that is very precise. All right, so in this section, our objectives are going to be to using properties of limits to evaluate a limit. We're going to develop and use strategies. We're going to use the dividing out technique, the rationalizing technique, and we'll take a look at something called the squeeze theorem. Right? All right, so first off, properties of limits. The limit function f of x as x approaches c does not depend upon the value of the function at c. Remember, that's the definition of a limit. It just simply says it just happens to be close to the value of f at c. Right? But sometimes it may happen, however, that the limit is precisely f of c. That is, you might end up with a function that when you're evaluating the limit, you can just apply c to the function and see what you get. Right? This technique is called direct substitution. In fact, it's what I did here. I just took the 5, plugged it in for x up there, and said 5 plus 2 is 7, 1/7, and I was done. Because I used a technique called direct substitution. Right? So the first thing that you always check when someone hands you a limit is you check to see if direct substitution works. But it's only applicable when you have functions that are continuous at c. So being able to look at a function and know whether it is continuous or discontinuous at a value c is an important thing to know. Right? All right, so let's look at some of our first, we're here, right? Our first properties of limits. Here are some basic limit properties. The first one says the limit of b as x approaches c is equal to b. The second one says the limit of x as x approaches c is equal to c. And the third one says that the limit of x raised to the nth power as x approaches c is just c raised to that nth power. Right? And so let's take a look at what this means. Right? So what would be the limit of 5 as x approaches 9? Well, the answer is 5. We're using this property right here. Right? That's what's being evaluated there. You'll notice that there is no variable in the argument of the limit. So it doesn't really matter what x is. The value of this expression is always 5, no matter what x is. If you're one of those people that has to have more, well, graph it. Graph the expression y equals 5, and what do you get? You have a horizontal line. So if that's 9, and we're coming in from the left, and we're coming in from the right, where are we? Well, we're at 5 on that y-axis. All right. What is the limit of x as x approaches 9? So now we're using this property right here. The one that says the limit of x as x approaches c is just c. So then this is going to be equal to 9. All right. How about this guy? What does this one say? Well, this one says, what is the limit of x cubed as x approaches 9? Well, now we're making use of this property on the end here. And that property says that the limit of x raised to the nth power, where n is a positive integer, we do have a positive integer there with 3, is just c, in this case 9 raised to the third power. And what is 9 to the third power? 9 times 9 times 9, 9 raised to the third power, I think 729. So these are our basic limit rules. They say that if you have one of these three, let me erase all the extra gobbledygook so we can talk about them. One of these three scenarios, if you're taking the limit of a constant, the limit is the constant. If you're taking the limit of the identity function, x, then the limit is just c. And if you're taking the limit of x raised to the nth, it's just c to the nth, where n just needs to be, at this point, a positive integer. Right? All right. Some more properties of limits. So basically what you should be doing is you're looking at these things going, oh, these are the rules that I need to know to do limits. So I need to memorize these rules. Right? And guess what? Here's a bunch more. Right? Let's read the ifs and the thens and take a look at this. So let b and c be real numbers. So b is just a number, c is just a number, any real number. N is a positive integer. So n's a positive integer, b and c are real numbers, we're good there. And let f and g be two functions where these two statements are true. That is, the limit of f of x is some number L as x approaches c, and the limit of g of x is equal to k as x approaches c. Right? We have 5 rules here. Rule number 1, the scalar multiple rule, says that if you have a scalar multiplier in front of your function, just simply find the limit of the function and multiply in that scalar multiple. So the limit of f of x is is L. So b times that f of x is just going to be b times L. Now the second one here is sometimes written as 2 different rules in some textbooks. This book writes it as 1 rule. It says that the sum or difference, that is the limit of f of x plus or minus g of x as x approaches c, is just equal to L plus or minus k, where L is the limit of f and k is the limit of g. And so we just put them together, find the limit, grind it out. Right. Third one says, take the limit of f times g, and you get L times k as x approaches c. Right? So we have the product of 2 functions where we know the limit of each of those 2 functions. And if we know the limit of each of those 2 functions, we just multiply those values together, the L times the k, and call it good. Right? Quotient rule says that if you have f divided by g, then the limit is just L divided by k. But what do we always worry about when we do division? K cannot be 0. So as long as k isn't 0, we can divide by k. L divided by k, we have our limit. And then the last one. Okay? Now the last one you might be looking at going, isn't that just this one up here? No, because this rule up here only works if it's plain old x raised to the nth. This one says that if you have some sort of a function, f of x, that you can then find that limit of f of x and raise that limit to the nth. Right? All right, so let's take a look at some examples here. Okay, so we're supposed to take the limit of this polynomial here. And so basically what we're going to do is we're going to make use of those rules that we have up there. So what I'm saying, and I hope you're saying, that if I were to apply these limit rules, I could rip this thing apart and rewrite this as the limit of x squared as x approaches 3 minus 2 times the limit of x as x approaches 3 plus the limit of 9 as x approaches 3. And the reason I'm ripping this thing apart like this is I want to get it down to a place where I've just got those rules that I had before to make my life easier. And so now I can say, okay, that first one is just the x to the nth rule, so that's going to be 3 squared. The second one is just the coefficient times the limit, so that's going to be 2 times, and that's the x rule, so that's just going to be c, or 3. And the third one is just, the limit of a constant is just the constant. And so I have 9 minus 6 plus 9, and I believe that's 12, right? So then the value of this limit is 12. Now, realistically, are you going to write all this out every single time? Or are you going to recognize what this is and go directly from here to this line and use direct substitution to get to where we need to be? Okay? So yes, the highlighted yellow piece right there is using the rules that we're supposed to use, the rules that we're expected to use. Okay? But as most things in math, once we learn the rule a few times, we start skipping it. Okay? I'm sure by now, if you had this as an algebra equation, you would just go straight to x equals 2. You'd never write the 1/3 times on each side. So once we see a pattern, we start skipping things. And this is just one of those places where we can see a pattern and start skipping things. What's that going to delete? Okay, all that. That's good. So yes, this is what's happening behind the scenes, but like with a lot of math, we don't always write everything that's happening behind the scenes. Right? And so basically what it ends up with is the direct substitution property is valid for all polynomial and rational functions with non-zero denominators. And so that's what we're going to use. We're going to use direct substitution all the time until it stops working. Okay? For example, here I have a limit or a rational function. I'm just going to use direct substitution and hope that it works. If it doesn't work, then I'll fall back on trying other things. But for right now, I'm going to see if it works. Direct substitution is going to turn this into 2 squared minus 4 divided by 2 plus 2. 2 squared minus 4 is 0 divided by 4, and 0 divided by 4 is 0. So then the limit of x squared minus 4 over x plus 2 is 0. Direct substitution, and I'm done. I don't need to do anything fancy. I don't need to do anything more than that, because I did direct substitution and it gave me a valid answer. It gave me a numerical answer. And when that works, it works. That's all I need to do. Right? And what it does is it gives us a couple of theorems about limits of different types of functions. And it reads, the limit of a polynomial and a rational function. If p is a polynomial function, so p is a polynomial function, c is a real number, the limit is just direct substitution. If r is a rational function, given by r is equal to p divided by q, p of x divided by q of x, and c again is a real number, then the limit of r of x is just direct substitution. The only caveat we have here is, what can we never have with a fraction? Well, we can never have a fraction where the denominator evaluates at 0, because we cannot divide by 0. Okay. The limit of a function involving a radical. Okay. So what do we have here? Okay, so now n is a positive integer, so we're taking a nth root, a positive integer root. The limit is valid when for all c, when n is odd, and for positive c's when n is even. Basically just the limit of a root, direct substitution. Now what is all this stuff about even and odd here, this even and odd business? Well, remember, you can't take an even root of a negative number. So that c must be greater than 0 for when it's an even number. Is that okay? Okay, so keep that in mind. This is about no roots of negatives. How about composition? Well, if you have two functions, their names are f and g, and they are functions such that the limit of g is known. Now stay with me here because this one gets a little bit complicated. And the limit of f is known, then the limit of f of g as x approaches c is f of the limit of g of x as x approaches c is f of l. Did you catch the connection between these two? Did you notice that they're not the same location for the limit? Did you notice that g of x is a limit that is at c, whereas f of x is a limit that is at L? They're not the same. In all the other ones that had two things in there, the addition and the multiplication, the division, it was always at the same value c. This one's different. Why? Because it's composition. The c is going to go into the g, and then what's going to come out of the g function? Coming out of that's going to be L, and then L needs to go into f. Because this inside piece right here, when we evaluate that and take that limit is going to be some number L. So then we have to have L be a number that is in the domain that is valid for that function f. Okay? So this is the first one that is different in that we have two functions f and g, but they don't have to evaluate the same number. They have to evaluate at the proper relationship for that composition. Right? And then we have the limits of transcendental functions. And what do you see here? If c is a number, a real number that is in the domain of the given function, direct substitution, sine, cosine, tangent, cotangent, secant, cosecant, exponential functions, logarithmic functions. Okay? Direct substitution. You want to take that limit, direct substitution every single time. All right, so we are just about out of time here. We're at 16 minutes. I'm going to stop this video. The next one we'll start here. We'll start taking limits. And as you can see, we have plenty of limits to take. Okay? All right, see you back here for part 2.